Now we're going to go on to MPI. The MPI for me is it was a bit difficult for me to create kind of hands-on for this because, yeah, the nice thing with OpenMP is we could have done things little piece by little piece. With MPI, it's a bit harder to do that. I think the code has to be a bit more complicated in general because we have distributed memory, etc., etc. But I did my best anyway. Do this, and then we'll just see how it goes. This one is actually not intended to be too long because I couldn't really figure out how to do some effective hands-on too well. So we'll just take it as it comes. And basically, in terms of MPI optimization, there's kind of two things you want to do. The first of those is to minimize the amount of communication you actually do, right? The whole idea is it's distributed memory, and because of that, you have to pass messages around, right? So those messages come at a cost, and you want to reduce the cost, right? How do you reduce the cost? You minimize the amount of communication you actually have to do, right? So basically, communication is overhead, right? Any communication you have to do means that there is overhead involved. The transfer time for any kind of message is basically the latency plus, we've seen this already, right? So it's basically latency plus the message length divided by the bandwidth, right? So how much information you can get through in any time. The latency is just a startup for any kind of message handling, and the bandwidth is how many bytes you can transfer per second, right? So when we have n messages, the total transfer time then is n times the latency plus the total message length divided by the bandwidth, right? But we can look at each of those individually and see, well, what can we actually impact ourselves? The first thing is that instead of sending a lot of messages, n messages, we could try and send one big message instead of several small ones, right? And that will help us with this n star latency, right? So that will reduce the total amount of latency that we have, right? The second one is we can actually affect the total amount of bytes. So we can try and reduce as much as possible the actual amount of information that we pass around. As much as we can, right? As much as it's possible for us to do that. The other thing is you can actually affect bandwidth a little bit. I'm not going to go into that today, but the actual bandwidth that you can get depends on the protocol, the MPI protocol that you use. That's a bit like high-end stuff. There's no real need to go into today, and we're not going to. So in terms of minimizing the amount of information that you pass around, you can think about decomposition of your actual problem, right? The first thing you'll probably do when you do MPI is just do a nice simple one-dimensional splitting of your problem. Cut it up into just one dimension, cut it like this. In that case then, the amount of communication that you do, so basically you have a couple of parameters involved in your problem. You say like it's a three-dimensional matrix, we'll say in this case. So you've got a halo because you need some halo information about your neighbors and things like that. So you've got a halo around, you've got a matrix of a particular size, so it's n cubed in this case. You've got some number of processors, and then in this case we have a cyclical boundary, right? So two neighbors in each direction, right? So a fairly straightforward little problem that we're talking about. In one dimension then, the communication would be just this simple formula, n squared times 2 times w and times 1 then, because we have one dimension. We could also split our problem into two dimensions. Again, you can do a little bit of work and you'll see that the formula will work out like this. Right? So basically we have two dimensions, and so that means different message sizes and different numbers of neighbors, etc. In three dimensions, again we can do the same exercise and we can come up with another formula for the same thing. And then we can compare them. And the reality is that once we go for this problem, because we have the three dimensions, we actually, this three-dimensional splitting of our problem is optimal when we have more than 11 processors. And so basically, these kind of considerations can impact how you decide to split up your problem, right? If these things are real issues for you. So basically, yeah, once you get to large numbers of processors, probably you want to think about exactly how you're going to decompose your regions. That can help you in minimizing the amount of communication that you're going to do. The other thing you can think about is instead of actually communicating something around, can you actually calculate it on the machine? It may be faster to recompute something rather than communicate it around to everybody. If the information is available to everybody, it may actually be faster to compute rather than to communicate. Right? So it's something you need to look at explicitly in each case, but that can be true as long as the information is actually available to everybody. So if several people can do it, you can think of like, you have a couple of options. You can do a parallel computation. Everybody does the same computation and gets its own answer. Or you can do a single computation and then a broadcast on top of that. That would be another thing you could do. And then all the other and the idea here is that the single computation and you have a broadcast, and while the other processes can do work while this first one is doing the computation. Okay, so you try and overlap these areas a little bit. And then the other thing, the last thing you can do, and of course this is the worst solution, would be to do a single computation on a single processor and have everybody wait for the result. Right? So that's not helping you at all. Everything else is just idle while you're doing this. So if this computation takes time, everybody just sits there doing nothing. The other thing you can do to minimize the communication is think about the actual architecture that you're on a little bit. Right? So we've got clusters of multiprocessor nodes. Right? So we've got this system where we have like a nucleus, like we have eight physical cores on side. So on a node like that, you could think about, well, I don't need MPI in everyone. There's shared memory on this node, so I only need an MPI process on each node individually. So you got one MPI processor on each process on each processor or hardware thread, depending on what you're talking about, of each node. And then you have to think about maybe how they're ranked or something like that. Personally, I think you're probably better off doing, in this case, there's 2 sockets to do 2 MPI processes per socket, because then you'd avoid this potential memory problem where you have to go from one socket to the memory on the other socket, and that's going to introduce this thing we saw in the OpenMP. So personally, I would say you can avoid that problem by putting 2 MPI processes on there, one on the first socket, one on the second socket, and then they each have the distinct memory space, and you don't have to worry about this NUMA so much, or at least to some extent. Right? So we can have one MPI process on each node or socket, and then you could potentially so basically, I don't know if you know this already, but the compiler can automatically do kind of OpenMP style optimizations. Whether it does a good job depends on the problem that you have. We could have maybe tried it earlier on our code. Our code was pretty simple, and it may have done a good job, but it probably wouldn't have, because it would have seen the ran function and went, I can't do any OpenMP on that, and would have done nothing for us in the end. So you could do automatic parallelization, or then you can do it yourself by hand with OpenMP, and then you end up with your hybrid code, the thing you would have seen the other day on Tuesday. And maybe only one root process does the MPI, and then the cache coherence. So we have the potential performance problems that we just talked about, these cache coherence and things like that we have to take care of them because we're bringing in the OpenMP. The other thing that you want to do is, so you have communication. You can't get around the fact that you actually have communication, right? Because you've split your problem up. What you can try and do is minimize the impact of that communication. So that's the other thing. First off, you try and minimize the amount of communication. Now you try and minimize the impact of the communication. The thing you should consider is that the collective operations are typically optimized by the vendor of the MPI library, right? So they're selling these MPI libraries, so it's in their interest to do a good job, right? The places where they can do a good job are typically in these collective operations, right? So if it's possible for you to use a collective operation to do the job that you want to do, then you should do it, because they'll have implemented it efficiently, right? So an example would be a broadcast. If you can use a broadcast, do. So they have particular algorithms that they can use for that. There's a binary tree algorithm, which is nice and load balanced, and everything spits out nicely. It's pipelined, and et cetera, et cetera. It doesn't actually result in the best total execution time. There's another one, an unbalanced tree, that will do that. I don't know too much about the details, but you get the idea that there are potential methods for implementing a broadcast. The vendor will have tried a couple of those and probably will have come up with what should be an optimal solution, right? So basically, you can always test how good their solution is. You can come up with your own algorithms using the MPI peer-to-peer, P2P or something like that, and see how does it compare in terms of performance. Typically, you'll do awful compared to what they can do. That's just how it goes, because they're the one doing the implementation. The things that they utilize kind of cleverly is the fact that MPI these days is typically aware of the architecture on the node. So it knows, for example, that for particular processes, it knows that they're on the same node. So rather than do the actual communication, it just knows that it can copy this piece of memory, to this location, and that's it. That's the communication is done. So these days it's pretty clever. It's aware of the architecture that's on site and takes advantage of it. And that's why sometimes it may seem like a good idea to do this hybrid programs, but actually when you do it, it doesn't have a big impact. It's kind of because effectively MPI is already aware of the hybrid nature of the program and has some tricks inside to minimize the impact of the MPI. And so basically back to the broadcast thing, you get a parallel execution on all processes on the shared memory. You do something special on the shared memory, or you can have the hardware broadcast over the network. So the rules generally are always use collective operations if it works for what you want to do, because that'll be the most efficient way to do it. Of course, you should always avoid all-to-all communication. Has a big overhead. I mean, they implement it efficiently, but if you need to use it, it's going to mean basically especially when you're talking about Prace resources at the large scale, if you have all-to-alls in your code, you're set for disaster. It's not going to work, right? So you need to figure out as much as you can how to avoid all-to-all communications. Because, for example, if you think about the big machines, like our huge cluster system in Jülich, each MPI connection has a buffer attached, right? So once I say I'm going to communicate with this guy over there, there's a little piece of memory that's allocated for a buffer for that communication between the two of us. If I have all-to-all communications, that basically says I'm going to communicate with everybody, right? Which means I have to allocate a buffer for everybody, because at some point I'm going to send a message to him and him and him and him, and so it allocates a lot of space. And the first thing that you're going to do is run out of memory. So that was discussed already the other day, but that's one of the things that will happen is you'll run out of memory. And so basically you don't want that to happen. And so as much as possible you have to try and avoid all-to-all. And that's on the cluster system. On the Blue Gene system, for example, you run into the problem that in terms of the physical network, it's actually very far away, right? So at some point, if you're communicating with everybody, there's one guy who's going to be really far away. And when you're talking about millions of processors, that means lots of hops on this special network that they have. It means like hopping a lot of places to get the information from one point to the other. It's going to have a huge impact on your code, right?
What do you mean far away?
I mean physically far away. So on the Blue Gene, it's kind of a weird network where basically it's a normal grid. It's 5 dimensionals, but it's basically a grid. So if you think about it in terms of, and there's no marker here, right? But you think about it in terms of a grid, right? So say we have like a 3x3, and we want one corner to communicate to the other corner, and the network is a grid system. So to get from one corner to the other, he has to hop to the neighbor on the right, then say, for example, the neighbor above, the neighbor on the right of him and above, right? So we had all these little hops. The bigger the grid, because we're talking about millions of processors, the more hops that are involved, and then all these people in between have to do something, right? They have to know that they have to communicate this message around, so it's overhead for everybody in between as well, right? So it has a huge impact on things. So typically, you try and set things up so that you only communicate with your near neighbors. And that's why these special algorithms are very important to use on that type of network, because it knows, the MPI on that knows about this network, and it will do it in a clever way. Right? So it doesn't have to communicate with everybody, just a few people around them. Okay? And the last thing is never to use MPI barrier. Right? So MPI barrier means everybody has to wait. It's a big global communication thing, and it has a big impact. Okay, there's some cases where you need to use it. If you don't have a parallel debugger or something, that's basically the only tool that you have to help you out with these things, right? So okay, if you're debugging, that's fine, but at production time, you shouldn't have any of these statements working anymore. The other thing about the impact is, okay, we have impact because we have the communication. We also have synchronization time. So the original formula was like this, but the reality is that we also have to think about the fact that we have synchronization time on the end. Synchronization time, well, what does that mean? It basically means that the receiver has to wait until the message is sent, right? So he has to wait some time, and the sender has to wait until the message is received. It doesn't even matter if it's blocking or whatever. At some point, it's going to have to wait to know that the message has actually been received on the other end. One of the things you need to avoid is the fact that this can bring serialization to your code. We'll see something related to that in a second. And of course, we also want to avoid idle time. Waiting time is idle time, sitting there doing nothing, waiting for something to happen on somewhere else. There are a couple of methods to try and do this. Non-blocking routines, which means avoid waiting on the communication at a particular time. Of course, you will have to wait for it at some stage, but in between, the message can be sent, and then hopefully you won't have to wait so very long. And then you'll also have to wait to free the request and for the buffers to be freed and things like that.